on the HOVA app.
Oh, perfect. Yep, you can. Sorry, guys. I was technical difficulties. Welcome. Hi, and welcome back to the AI ML Data Science track for DataCon LA 2020. I'm Emily Shoaf, your host, and joining me today as my co-host is Aaron Atea. We will be moderating the chat and QA for you during this session. Our speaker, Matthew Wells, is a data scientist at Cedars-Sinai Health System with over 10 years experience working in the healthcare industry, both domestically and internationally. His work is focused on predictive modeling and pattern-based analysis to clarify and resolve complex issues for the healthcare system. Some of his projects include patient likelihood of C-section prediction, patient flow simulation, and the length of stay prediction for COVID patients. Today, Matthew will be speaking about real-time prediction of C-section risk for laboring mothers. Matthew, I'll let you take it from here.
Great. Thanks so much, Emily. All right. Okay. So thank you all for joining me today. Really appreciate everyone coming out here to hear me talk about this. Just a couple of quick disclosures about this. First of all, I have to say that all opinions I represent here are my own and not my employer's. And additionally, any sort of products I might talk about in here that we use, I have no financial stake in any of them. So getting that out of the way, I just kind of want to run everyone through for about half an hour this case study of what we've done so far with the C-section risk prediction tool that we've put together, and kind of give you a broad feel for everything involved in that project, and then I'll take questions after that. So to get started, my hope for this is really that there's something for everyone here. So I'll kind of touch upon some stuff that people who came here to hear about healthcare focused things might be interested in it. There are some sections here that are a little more technically focused. And then there are some sections here that are a little more focused on predictive models and things like that. So my hope is that everyone gets something out of all of that. So the different things I'll cover today are, first, I'll give a little background on how the project came about. Then I'm going to talk about the development cycle and how we've built and rebuilt this model and how we decided or made different decisions about how we were going to model things out. I'll talk a little bit about the results in terms of how accurate or inaccurate our model was, certain populations or different phases of the project. Then I'll talk about, for lack of a better word, productionalizing this, trying to turn it over from a model that we built and trained into something that we can then feed back to clinicians and help them make decisions. And then finally, kind of plans about what's happening next or what we've been working on in the background for this model. So first, to get into that project background here, I wanted to talk a little bit about the data science team at Cedars-Sinai. And so we sit within Enterprise Information Services, which is kind of all the technical things related to Cedars-Sinai. That includes about 500 to 600 people, I believe, in that department. Within that, there's Enterprise Data Intelligence, which is responsible for things like reporting, the Enterprise Data Warehouse, some research-related data, data governance, and then finally my team, the data science team. And so we're responsible mainly for predictive analytics in the hospital, things like simulation or optimization as well. And so over here on your right, you'll see this logo that I'm going to continue with throughout the presentation, Alex Observe here. And so just to give you a little bit of an understanding of what that is and why it's going to be in every single slide here, Alex is the automated learning by example platform, and that's something that we've built. It's our custom-made platform at Cedars-Sinai that we use for all of our predictive analytics and models. And each one of our different projects gets its own sort of flavor or its own branding. In this case, we've called this project Alex Observe for Obstetrics here, and that just kind of fit with it. So that's why you're going to see that throughout this presentation. So where did this project come from? So at Cedars, there is a master's degree in health delivery science. And actually, I should say that I'm right now in the second to last trimester of this program myself. The reason I got involved in this program is actually because one of the former students for her capstone project began to build up this project, and that's actually where it came from. And so you'll see here, I pulled from the website for the Masters in Health Delivery Science, the different capstone project examples. And so you can see we have things like program evaluation of clinical decision support. We have reducing intraoperative costs through supply standardization. And then finally, that one with the hyperlink down there, machine learning in labor and delivery. And so when you click on that hyperlink, this is what gets pulled up, is a little more detail about the principal investigator, Melissa Wong. And so how this came about was she had this idea a little over 2 years ago and said, hey, I'm really interested in looking at our ability to predict risks of C-section for laboring mothers. Is that something we'd be able to do with machine learning? And I was lucky enough to get assigned to the project and began working on her with it. And so that's where the development started with the project. And so ultimately, as we built this project out, we had to establish exactly what our goal was. And so what we came down with was that cesarean delivery can be a life-saving procedure for both mother and baby, but it also presents increased risks of morbidity for both. So it's important to consider both the benefits and risks before deciding on whether you should do a cesarean delivery. And so the purpose of this model is to take all that information and all of the decision-making that goes on about what informs whether or not a mother should have a cesarean delivery, and see if we can put that into an algorithm and say, well, this is what we think the likelihood of a different delivery method should be for a given mother in labor. And so as we got into the model development, we started with asking, okay, well, what's been done in the past around this? And so we focused on a couple of studies that looked at a whole bunch of different factors. And so some of those factors were things like the obstetric history, i.e., has this mother given birth before, and what's some important information around previous births. What is the age of the mother? What comorbidities does she have? What's the ethnicity, height, weight, things like initial cervical exam there, gestational age, fetal ultrasound. And so what they would do is combine all these different variables into a predictive model, and it would come out with a resulting score that says, this is what we think the risk of C-section, or the likelihood of C-section delivery is for that particular mother. But what you'll notice about all of these things is that these are all factors that are measured at or before admission into the hospital. So keep that in your mind as you think about this, because I'll come back to that in a couple of slides to talk about what we did to build on top of that. But before I do that, I thought I'd share how these models ended up doing and what they came out with. So using all those measures gathered together, there were a couple of models that we focused on that we looked in the literature. One of them built this nomogram, where you input your different features about this particular mother, and it comes out with a score for how likely she is to have a C-section. Similarly, this other paper built this sort of risk calculator here based on all those different factors involved. And these different models had AUCs, or areas under the curve, of 0.69 and 0.76 there. And so how were we going to be any different than these things? So we said, okay, well, let's take all those admit factors, and then let's go a little bit beyond them and start to look at the intrapartum factors, the things that happen after a mother is admitted to the hospital, but before the baby ends up being delivered. And so we said, let's look at fetal heart rate during the course of labor. Let's look at the medications administered during the course of labor, whether or not the mother got an epidural, and then intrapartum cervical exams, and see, can those things make a difference in the accuracy of a model and inform a little better on the prediction. And then the other thing we had to consider is, as we started to look at this, and Dr. Wong presented this option to us and we started digging through the data, we kind of said, all right, the thing is, the goal of this model isn't to carry forward what's been happening in history. It's to try and improve upon it, try to make the results of these deliveries more equitable, or lower the C-section rate in where possible, or reduce variation, because as we know, where there's variation, there's opportunity. And so we looked at all of the births here at Cedars, and we said, okay, well, between 2012 and 2019, there were roughly 45,000 deliveries by 469 different physicians at Cedars-Sinai Medical Center. And then we said, okay, well, we have a couple of high delivery providers, 103 providers who had greater than 50 deliveries in that time. And if we look at specifically within that group, we found 36 providers that had less than a 24% C-section rate. That 24% is based on a national standard that the obstetrics department is trying to adhere to. And so that was sort of our goal, was anyone below that, that's going to be our target group. We think they're performing at what we want the C-section rate to be. And so we're going to model what would happen essentially if those physicians were to go ahead and if their C-section rate was to be carried forward for all deliveries. And so when we looked at that group and we said, okay, let's take specifically those physicians. Let me move them over here. We take that little subset. We find that there were about almost 12,000 babies delivered between 2012 and 2019 to that group. So still a very robust data set for us to build a model with. The last thing we had to do was say, okay, well, these doctors might have low C-section rates, but let's make sure that those are still safe, that they're not too low. And so we took a host of other measures and looked at mother morbidity measures and infant morbidity measures, and then also admissions to the neonatal intensive care unit. And we found that none of these measures were significantly different between those two groups. So we felt confident that this group that we're looking at, the sort of target physicians, was a good group of physicians to model going forward with this, this particular predictive model. And so then, having considered all those things, we went and wrote down and sort of drew out, what does the roadmap look like very, very roughly in terms of how does this model get structured? So in the yellow is sort of the start over there. After we've created our population group, what do we do then? And so after filtering for those 11,763 births and using that as our training, or excuse me, what we're going to use to build the model, we then pull in all these factors available at admissions. And I'll give a little more detail on all of those factors in just a second. Then we take that, we run it through our automated machine learning process, where we have a whole bunch of different models sort of compete to come out with which one is the best at predicting this particular task. And then we take the best of that model and we say, all right, well, let's see what the results of that prediction were, and then go ahead and combine them with the real-time factors, those things that are coming in after admission, but before the baby is delivered. And then we again take that information, run it through another automated machine learning process, take the top model from there, and then we finally get our predicted C-section likelihood for all deliveries for those target physicians grouped at 10-minute intervals. So what were the results of those models? And so what came out of that? First, we took a look at those admission factors and we said, well, how good are we doing against what we've seen in the literature? So first, let me run you through everything that we included there. So we got the admission measures for the target population, and that included things like the initial cervical exam around dilation, effacement, and station, the gestational age, the mother age, the prenatal measures. So we looked at prenatal visits and looked at aggregates around blood pressure, BMI, and weight. And then finally, things like pain scale score when the mother came in, her temperature when she was admitted, and then pulse at the time of admission. We then went and ran it through all those models. This was the automated machine learning process that I kind of talked about before. So that considered models like random forest, XGBoost, generalized additive models, logistic regression, extra trees classifier, elastic net regression, and on and on and on from there. And so after running it through all those models, we found that a random forest model ended up doing the best. Our AUC for that particular model was 0.75. So, at the higher end of what we'd seen in the literature, but we really didn't exceed it, nor were we necessarily trying to exceed what had been published before. You'll notice that our sensitivity is very good there. And so in this case, what that means is our model is very, very good at picking out non-cesarean vaginal deliveries that came through and identifying those correctly, What it's not so good at yet is identifying cesarean deliveries. You'll see over here in the 2x2 I have that of the cesarean deliveries, it only correctly identified about 1 in 7 of those. So before I get into what we did subsequent to that, I want to run through what features were most important for the admit predictions. And the way we identify these is we say, let's look at it on a permutation basis. And so what we found with that was that dilation was the top most important measure in terms of making that determination. Then gestational age, BMI at admission, mother age, station, effacement, and on down from there. And just a little bit of a note about how this method actually works is what happens is we take a measure after we've built the model and we say, okay, well, let's take all the values in that particular feature, shuffle the values, and then see what that does to the model. Does it make it less accurate? And so the models that it tends to make, or excuse me, the instances where the feature made the model less accurate are the ones where we know, hey, that feature is pretty important to the model. So then we take all those different features after we've looked at what happens when those values are shuffled, and then we quantify how much it changed the model, and then we scale it to 0 to 1. So that's why you see dilation as a 1 over here, and then finally on down to temperature at like a 0.17 or something like that. So then the question becomes, okay, well, what happened when we started including intrapartum factors? What happens when we look at what we've built on top of what exists in the literature today? So again, we got those continuous measures for target population. And so now these additional factors that we included beyond the admit time prediction were things like dilation, station, and effacement, the cervical exam measurements, but we look at them continuously throughout the stages of labor. We look at minutes into labor, so how long has the mother been in labor? What medication has been administered? Is there a Foley catheter present? And then things around fetal heart rate patterns to see, are there accelerations or rapid decelerations in the fetal heart rate? Again, same host of models that we tried out, but in this case, it was extreme gradient boosted trees that came out on top with an AUC of 0.96. And so this was a lot better than what we were finding at admission. Again, our sensitivity was really good, but our specificity is really what's going up here. And to be clear about that, you'll see there are a lot of numbers over here. It's much, much higher end than we were looking at before. And the reason for that is that now we're not just looking at every patient, we're looking at every patient in 10-minute intervals and looking at how well our model does at those 10-minute interval marks for how good it is at predicting the actual there. And so then again, if I look at the feature importance here, you'll see that the most important feature by far is what was the prediction at admission. And I think that makes sense in a way that, it sort of is a base guiding principle to say, okay, well, the admit prediction was such and such value, and then the rest of this kind of builds on top of this. What is the dilation measurement at this particular time, and how might that affect it? What's the station measurement and the effacement? So you'll see that that cervical exam is hugely important in making these predictions and sort of updating the model predictions after a woman goes into labor. Again, we use the same sort of methodology here. I thought I'd just reiterate exactly how that methodology worked. But to be clear about that, one of the things you might be thinking right now is like, okay, Matt, yeah, you did really well when you were predicting over time because you probably started to get these measures out here where labor went on for a long time and you were just predicting correctly because there's so much information for a long time. So you might think that I'm padding my stats a little bit, which, that's fair. The AUC of 0.96 is probably a little high. So in order to sort of validate that, what we did is we went through and say, okay, well, let's look at how we did at each given hour interval. And so what this is a breakdown of on a 100% scale at every hour interval, what we got right. In the case of the dark blue here, we said these were non-cesarean deliveries, and we were correct. With the light blue here, we said these are going to be C-sections, and we were correct. With the case of the dark pink, it was C-section prediction when it was actually a vaginal delivery. and then the light pink is the inverse of that. And so if we look at it at just one time slice here at 4 hours in, we see that the sensitivity is still very high at 99.4. The specificity goes down a little bit, but still pretty valuable in terms of how well it does in making that prediction there. So this sort of gave us confidence that what we were seeing in terms of an AUC was not just an artifact of the fact that we just had predictions that were going out for a long time where we were doing very well with those. So productionalizing, how we sort of are turning this model around right now into something that might be useful in terms of feeding it back to the clinicians. So to give you a sense of like what I've spent maybe the last 6 months of this project on is trying to turn around these different queries that I wrote, these SQL queries, and going from data that's aggregated every midnight for our training set and trying to convert it into something that'll work against a real-time data set that we can turn these pieces of information around in 5 or 10 minutes. So it's valuable to the clinician in real time during the course of labor. And so I broke them down into the different major queries that I have here and how I had to change them in order to sort of fit with this real-time model. And so this first piece, the prenatal info, where we're looking at stuff that happened with the prenatal visits, really I didn't have to do too much to this because this can still go against that previous data. We don't need this to be updated because those prenatal visits happened 3, 6, 8 months ago. So all I had to do was limit to the current patients in the labor and delivery unit right now. Demographic information was pretty similar in that I was just limiting it to the new patients, but also because I wanted to get it on patients that may not have prenatal visits, I also had to look at demographic information in the real-time data and change to a new data source. Location information, all that stuff about getting it from labor and delivery. Again, similar sort of changes, but I had to restructure it because it was a different style of table and the information was coming in differently. And then medication administration, and then flow sheet measures and events, those things that come in real time. Those I had to not only restructure because they were different tables, but also I had to consider additional data transformations because, the data types might change for some of these from numerical to string values, or we didn't have the same lookup tables for some of these things. So I had to completely alter a couple of different things. And one of my biggest personal takeaways from this project was that it took me a lot longer to migrate from a completely different database to a real-time one. There were a lot more challenges than I thought I would face in doing that. But we ended up getting it done. And so then over the summer, we built a dashboard on top of that in Tableau. And so the resulting dashboard looks something like this. So this is a mock patient I brought in here. And essentially what we're doing here is we're allowing the physician to pick a patient, and you can see over the course of labor here for each hour into labor, or excuse me, each 10-minute slice, you'll get a different value. And to be clear, this light line that you can kind of see in the background is the actual prediction, and the darker line is an exponential moving average that we've built on top of that. And the reason we do that is because we want to make sure that we're not just looking at the most recent prediction, but we're also sort of taking into account in some fashion what was predicted 10 minutes ago or 10 minutes before that, and trying to make sure that those are baked into our ultimate predictions as well. And so to be clear on this, a value of 0 is a C-section prediction for this particular person in labor, and then a value of 1 would be a predicted vaginal delivery for, with the red indicating we're closer to 0 and the blue indicating that we're closer to 1. Now, you look at this and you might say, okay, great. Well, we know what the prediction is, but how does that help a clinician? Because really, we're not trying to replace clinician decision-making. We're really trying to augment it here. We're trying to provide information that isn't going to make that decision in lieu of a clinician, that will help that clinician make that decision and maybe inform that decision better about a C-section. And so what we did was we said, you know what, let's add a little bit more information to this. Let's pull in for this particular patient what the most important feature was at a given time. And so I've just shown this at a couple of hour intervals here, but you can see for this mock patient here, the simulation was a okay, it was a very low prediction here, or a prediction of C-section, but it went up, and the most predictive reason here was probably because of administration of dinoprostone is met here. But then we see it start declining after a couple hours. And that's because the dilation was still at 0.5, which is pretty low for this course of, or at this time in labor. But then you see it come back up again. And the model seems to be making that prediction based on the introduction of a Foley catheter at this point in labor. So that's kind of an where we are now in terms of prospectively evaluating this model and looking at how we might roll it out and help inform clinical decision making. So the last piece I'll talk about, and I've named this ongoing work, and I don't want to give the impression that it's stuff that entirely we haven't done yet, because some of this is stuff that we've looked at already, but we're continuing to build upon and hope to improve upon. So what are we doing with it now? Like I mentioned, prospective validation. Dr. Wong and I particularly are looking at this to say, does the data look right? Are we getting the right data types? Is it coming in consistently? Does it match the history of data that we have in production for what's coming in on batches at midnight? Does the timing look right? Is it all there? And I will say that as we've developed it, we've definitely found instances where, you know, something went wrong with the code and I had to improve upon one or more of these things. So it's been very much an iterative process in that sense. But then we also have this larger question of like, okay, you know, if all the nuts and bolts of it are starting to look right, let's think about, you know, prospectively, you know, when we looked at historical data, that AUC looked great, but that doesn't mean anything if the AUC isn't as good or better prospectively for patients potentially that are in the hospital right now. And so, you know, we're looking at what our accuracy looks like, but then also we're looking at, you know, what is the prediction behavior? Is it jumping around a lot, or does it sort of settle in? But then also there's an issue of timing to say, you know, we want to identify prospectively, when is a good time to start trusting the model? Is it 4 hours in? Is it 2 hours in? Is it 6 hours in? And how we potentially judge that. One of the big things that honestly I could do a whole nother talk about this topic. And one of the sort of goals of this model was to say, can we use this to potentially reduce that variation that exists at subpopulation levels, and say at race or ethnicity or differences that might happen by primary language spoken, is there a way we can bring those in line and use a model like this to reduce that disparity? And so the way we think about it is these fall into two different categories that we think about. There's the quality of service harms that might happen when prediction accuracy or other outcome metrics are not equal within groups. And then there's allocation harms, when opportunities or resources or information are withheld or offered at different levels to different groups. And you can see how those two sort of go hand in hand. If you have a model that's more or less accurate or predicting different things for different groups, you know, it might mean that decisions are made in different ways for those groups that might unequally allocate resources. And so what we've done there is to look at different mitigation strategies. And so we've built whole other dashboards on previous data or historical data to kind of look at this. But now, as we start to look at that prospective data, one of the things we're looking at introducing is a couple of algorithms and metrics from this Python library, fairlearn.io, which not only has measures of potential accuracy compared within groups, but it has different strategies for how you might mitigate that if indeed you find that your model is producing different levels of accuracy that you're not comfortable with within different groups. And so then lastly,
that is the perfect time to cut in. We've got about 9 minutes left.
Okay.
And I do have a question from one of our viewers that is in line with what you were just talking about. Okay. It was this user asked, is race taken into account so that the model can counteract a doctor's bias regarding BI, POC women? And how can we avoid cases similar to, unfortunately, the Kira Johnson incident that happened earlier this year?
Yeah, that's a really, really good question. And so what I will say about it is that we do not explicitly include race in the model decision making, because if we were to do that, then the model would potentially carry forward any biases that we might be seeing in the historical data, in terms of, essentially the model would then be saying, oh, okay, well, if you've included race, then the model's going to look for interactions that might have happened specifically to white patients or specifically to Black patients, and start making it decisions based on race in the way that they had been made previously. And we weren't comfortable with trying to carry forward decisions that had been made previously based on race, for all those reasons that were talked about. Now, I will say that it is something that we consider, and it's something that we are very closely monitoring the accuracy of, because ideally, what we would want the model to do is make the same decision for a white woman as it would a Black woman, as it would an Asian woman, regardless of race, And so what we were trying to monitor then is it doing that? Is it making those same decisions across race, across ethnicity, across any number of factors that we would be concerned about, that we don't think there would be some biologically plausible mechanism for a differentiation there.
Awesome, that was a great answer. Another question is, did you try balancing the classes? It seems like the original data is quite unbalanced.
Yeah, that's a really good question there. Our sort of rule when we look at those is, class imbalance is a big thing, and it is, especially in healthcare, where people are asking us to identify potentially sort of never events or events that happen very seldom. And when we get below 5 to 10%, that's typically when we're trying to look at balancing the classes there. In this case, because we didn't really get to a place where we were getting below 5 or 10% with those, I believe, we weren't trying to do too much with balancing the classes there.
Okay, and another one that just came in, are there cases of physicians or surgeons not agreeing with the model result and wanting to go with a completely different decision based off of their experience?
Yeah, I will answer that by saying I'm sure there will be. So we haven't rolled this out to a larger group of physicians right now. It's in a sort of prospective validation phase where we're just looking at what's coming in to make sure we're comfortable with the ultimate product being something that we're comfortable rolling out with physicians. And then there's a number of sort of hurdles in terms of medical legal stuff that has to happen there. So we haven't gotten to that point yet. I will say about that too. Honestly, like I'm comfortable if someone has looked at the model, the decision the model has made, and why it's made that decision, and saying, no, I don't agree with this. Because at the end of the day, it's that clinician's decision, and I'm simply trying to inform that decision better. I'm not trying to replace it.
Okay, perfect. And then actually the next question, we probably have time for one more and then closing statements. This question is asking, does your framework try to use any deep learning models? And as we know, the pros and cons of deep learning models is sometimes you lose the decision-making criteria within the model. And so is that something you're staying away from because of all the reasons you just stated? Or is that something that the model will incorporate at some point?
Yeah, that's exactly right. We tinkered with the idea of building a deep learning model, something like a long short-term or a recurrent neural network type model, but exactly like you mentioned, the trade-off there is that we lose some of the visibility into the decision-making process and that transparency, which is hugely important to this particular one because we're trying to augment a lot of what's going on. And, with an AUC of 0.96 for the entire, and then probably like 0.93 or 0.94 at any given cut point in the continuous model, we just felt like the trade-off in terms of like getting a little bit more accurate just wasn't there in terms of losing what we would in terms of transparency.
Okay, so we have about 3 minutes left. Are there any closing statements that you would like to make, or would you like to take one last question?
Yeah, I'll put my information up here in case anyone wants to reach out to me. Again, thank you all for listening to my talk here. Please, please, please feel free to reach out to me with any questions you have. If you think there's things I didn't address here or didn't address enough, please let me know. I'm more than happy to talk about this. I kind of love talking about all this deep in the weeds stuff about modeling, particularly around this kind of project. So that's it.
Very cool. So we have time for actually one more then.
Oh, great.
Do you have any features on the physicians attending? Maybe some of the physicians are more likely to recommend a C-section. So this kind of goes into physician experience and
Mhm.
preference based off of their experience and features put together. I think this is the
Yeah.
last one.
No, that's a great question too. And what we found is this is a particular area of interest for the obstetrics department, is trying to rein in some variation there in terms of different physicians and their C-section rates. It's a particularly tough topic because Cedars-Sinai is a pluralistic model in that not all the physicians are employed at Cedars-Sinai, and so in hospital systems in which they can sort of just put down an edict about the way things are done, that's not really how we operate. And the idea is that each physician makes the decision on her or his own clinical basis, and that their decisions are based on and they make these decisions sort of upfront with their patients. So yeah, that's sort of a long-winded answer about that. But I would say yes, and that's ultimately our goal, is to just sort of like try and rein in some of that variation potentially by providing more information about what's going on.
Very cool. Well, thank you so much for your informative presentation today.
Oh, thank you
And
for hosting.
and to all of our viewers, please reach out to Matthew if you have additional questions. If you posted something on Wova that was not answered, we will make those questions available to him. All right. Well, I guess this is the end. Do you have any last comments? Sorry, timing. I'm
No,
a little quick.
Emily and Aaron, thank you so much. I appreciate it. I know you guys are volunteering to do this, and it's great that you're doing it. So thank you. See
Bye.
y'all.
We'll see you all soon. Bye.